we decided at the end of our last class that one of these structures was different than the other three, right? And the different one was the set symmetric difference example. Right? So by the time we got to the end of class, the consensus, this was a unanimous vote, was that that structure was different than the other three. So this was the odd one out. But what I want to give you an opportunity to do for the first phase today is just to get some practice using these tables to do algebra. And when I say do algebra, those are the things like simplifying expressions, solving equations that we typically identify as being algebra. Just not using numbers and arithmetic, but using these abstract structures. And having a multiplication table is the most explicit way to define an abstract structure. So here's the plan. What I'd like for you to do is to get into your numbered groups again, so 5, 6, 7, 8, 9, 10. And I have 3 algebra tasks for you to get started. One of them is a simplify task. So, simplify the expression xz, the quantity, raised to the 5th power. And do it for both of these different structures. See if you get the same answer, see if you get different answers. Also answer the question, what cancels x in each of these structures? And then third, solve this equation for r. So we're thinking of r as the unknown here. xrx is equal to x. Okay. So those are your tasks to work on with the members of your numbered group. We're going to take maybe 15 or so minutes, maybe 20, until you're done, to get those 3 done. And then I want to push forward to a multiplication table that I gave you on daily work 4. So I'll also give you back your work from daily work 4 as well as 3, so you have your previous answers to look on. The goal, again, here is to get you used to working with an abstract structure. And in these examples, you get the whole structure right in front of you in this table form. And so it gives you everything you could ever need to know about how to do algebra with this stuff. So if I asked you, for example, to simplify xz to the power 5, let's say in this table, how did you actually do that? What's the first thing that you did? Yeah?
I broke it up into 5 separate xz's.
Okay, so you wrote out the 5th power as xz 5 times. So xz. Now I have to write this all 5 times. xz. Okay, which is good. We want to do that. Because, by the way, what should we not do? Maybe you had this instinct, and then maybe you caught yourself. But what would, let me put it this way, what would a freshman mathematician want to do here?
X to the 5th.
They would want to distribute the power. Why shouldn't we do that? If we distribute the power, we get x to the 5th, y to the 5th, or z to the 5th, sorry. How do we know that that's not necessarily the same thing as this? Yeah?
You're multiplying all the x's together and then all the z's together.
We're getting all the x's together and all the z's together.
Rather than x times y.
Does that always matter?
You don't know if it's
Commutative. There's the key word, right? If we happen to know that the operation in this setting were commutative, then it wouldn't matter if my x's were together and my z's were together. I could just make them together, and it wouldn't change my answer, right? In other words, I could just push all these z's out to the right side. I could push all the x's off to the left side, and it wouldn't change my answer. But if we don't know we can do that, then we shouldn't follow this instinct. And you all didn't, which means good. You're learning. But let me rewind a second and come back to an observation that I heard Sarah make in your group, which is looking at these tables, what can we say about whether or not these operations are commutative? Do we have the commutative property in one or the other of these settings?
Yeah.
Yes. How can we tell? What's the tell here for commutativity?
If they reflect along the diagonal.
They reflect over the diagonal. So, right, because we've written out the elements here in the same order on the top row as we have in the column, E, X, Y, Z, right? It means that a commutative operation will be one that's symmetric across this main diagonal. So, for example, this Y that's here and that Y that's there correspond to one another. This Z corresponds to that Z, and so forth. So, the table on the left has that symmetry, right? Every element on one side of the diagonal is the same product on the opposite side of this main diagonal. How about this table? Same. It works both ways. So in both of these cases, both of these tables, we have a commutative operation. So that actually means, I interrupted our evaluation of this xz to the fifth to make this point, but that means that if we had succumbed to our freshman sensibilities and distributed the power, we actually would have come out all right in this example. But you caught yourself and you didn't do it that way, and that's how I'd prefer you do it. Because commutativity, as we'll find out, is a property that very often is not true. There's another property that we would also need to be true in order to conclude that this is equal to x to the fifth, y to the z to the fifth. And that property has to do with these parentheses that are littering my expression here. Yeah. What's the name of the other property? Say it louder.
Associative.
The associative property tells me whether it's important where I put my parentheses in an evaluation that has 3 or more elements combined together. Right? So if this were, well, let me say it this way, and you can consult your daily work for this if you want to. What does the associative property for an operation say? How does it read? So there's this equation that goes into the definition of the associative property, right? That says that A star B, if I do that first and then I do star C, I get the same result as if I had done the second and third together, B star C, and then put the A star out in front. So it doesn't matter where I put these parentheses. And when an operation has the associative property, it is clear what we mean if we just write the thing without parentheses, A star B star C. In other words, this expression, A star B star C, is unambiguous. Its value is unambiguous when my operation is associative. But if my operation weren't associative and I wrote this down, it would make a difference if I decided to evaluate this star first or whether I decided to evaluate that star first. So if we're ever working with a non-associative operation, always have to have parentheses in any expression that involves 3 or more evaluations. But when it's associative, those two give us the same answer. But there's one more piece to this definition that I want to put in here, and that's an answer to the question, which elements, A, B, and C, must satisfy this equation in order for the operation to be called associative. We're just missing a clause here. That for all clause is important because it tells us what is the burden of proof. If I want to prove that an operation is associative, I need to show that this equation is satisfied not just for a random A, B, and C that I might select from the table, but I need to show that it's true for every A, B, and C that could possibly be selected from my table. So in our examples over here, A, B, and C can each be one of 4 different elements. So if I have 4 choices for A, 4 choices for B, 4 choices for C, how many combinations would I have to check if I were brute force checking that this were an associative operation?
12.
4, actually it's worse than that. 4 times 4 times 4, I'd have to check 64 different cases if I were checking this straightforward by hand, brute force. Maybe I'd tell a computer to check all 64 of them, right? But that's a pretty high bar. Right? That's a high burden of proof to show for all A, B, and C. So I just want to get that out there. If we wanted to convince ourselves that these operations were associative from the tables, we would have an awful lot of checking to do. It's much more challenging than showing commutativity. Where commutativity, we can just look for symmetry across the main diagonal. We can come up actually with examples of operations that are associative but not commutative. One such example is matrix multiplication. Matrix multiplication is associative, but in general, it's not commutative, even if it was for these 4 matrices. Commutative but not associative, that'll take a little more thought to come up with, because a lot of the examples of non-associative operations that we know, rather than being commutative, they're actually anti-commutative. Things like subtraction of integers, right? Subtraction is not commutative, but it's anti-commutative. If we reverse the order of a difference, it changes its sign, right? And subtraction is not associative for that actually exactly same reason. Same thing with the cross product of vectors in 3 dimensions. Is not associative, but it is anti-commutative. If you reverse the order of a cross product, you get the opposite vector in your cross product. So it's a little harder to, the examples that readily come to mind of non-associative operations happen to be anti-commutative. But it's possible that there are examples that are commutative. So if we're convinced that this operation is associative, then we can just remove all these parentheses and we can move forward with our lives from there. But I suppose even if we weren't sure that it was associative, what we could do is apply the order of operations. And I saw a lot of your groups do this. That you looked inside the parentheses and said, well, what is xz? So what is xz in this example? It's e. And so if xz is equal to e, then this is just, this is just e to the fifth power, or e times e times e times e times e. And what is that? That's e. After all, e operating on anything is just going to leave it unchanged. Right? So it operates on itself. It leaves itself unchanged, even if you do it 5 times. We should also probably check that this x to the fifth, z to the fifth also gives us the same answer. So here's a question. How would I do x to the fifth by looking at this table? So yeah, so using a table to find a power of an element, we'll just take it one multiplication at a time. X times x is going to give me y. So y is x to the power 2. To get x to the power 3, I need to multiply that by another x. So that's going to give me z. So here is x to the power 3. X to the power 4 will be that times x. X to the power 4 gets me to e, which seems meaningful. I'm going to put that off to the side. Right? X to the power 4 was equal to e. So what's x to the power 5? E times x. But e is our identity, right? So e times x is going to give me x. So x to the fifth is just going to be the same thing as x. What's z to the fifth going to be? It's going to be z, and I want to dwell on that observation for a moment. Because when we were first putting these tables together, when you were first putting these tables together in our last class, you had to make a decision on which element you called x and which element you called z. Did it matter? What, if anything, is the difference between the role that x plays in these tables and the role that z plays in these tables? It looks as though they play the same role as one another. After all, if you think about the complex numbers here, for example, I and minus I within this multiplication structure all do the same things. When I square them, I get -1. When I raise them to the fourth power, I get 1. When I do x times y, I get z. When I do z times y, I get x. Right? So they're serving the same function within their respective structures as one another. So everything that x does, z also appears to do. Right? So z to the fourth is also equal to e. And therefore, z to the fifth is equal to z, just like x to the fifth is equal to x. So there's also kind of an internal similarity, not just a similarity between these different structures, but an internal similarity between how x behaves and how z behaves. And that's actually also true in this structure, right? X is its own inverse, z is its own inverse, right? And they commute one with another. But then if we do xz, we do get the identity. So whichever way that we do this. All right, let's answer these last couple of questions, then we're going to move on, and I'm going to, what the sociologists call, trouble the concept a little bit, get us out of our comfort zone. But first, what cancels x in this structure? We've already seen it, Caitlin.
Z.
Z cancels x, and how could you tell?
Because when you do the x row by the z column,
Mm-hmm.
it gets you e, which is the identity.
It gets you e, which is the identity. So in order to answer the question, what cancels x, what do you have to know first? So you said, go to the row that x has, right, and look for, in that row, what am I looking for? I'm looking for the identity. So before you answer the cancel question, you have to answer the identity question. Right? We can't cancel something unless we know what cancellation is supposed to leave behind. Right? And cancellation is supposed to leave behind an identity, which, once we know it's e, we can look for e in that row and say, oh, what cancels x? Z. Does it also cancel x on the other side? So this shows that it cancels x on the right. Does z also cancel x on the left? Yeah. How do you find that information in this table? Look at the x column instead of the x row. So look down the column of x. Here's e. Oh, yes, z once again. All right. So z cancels x both on the left side and on the right side. So on this right, z cancels x. In this case, what canceled x in this structure? X canceled itself in that structure. And that was, remember, how we discovered the essential difference, one essential difference between these two structures, is that in this structure, x is its own inverse. In this structure, x's inverse is different from x. Right? So that was probably the biggest indication that we had that these two structures were in fact different. In this structure, everything cancels itself. X cancels itself, Y cancels itself, Z cancels itself. Over here, E and Y cancel themselves, but X and Z cancel each other. So that's the fundamental difference. Finally, how did you solve the equation XRX equals X? Solve it to get R by itself. What were your steps there?
Cancel Z.
So yeah, once we know how to cancel X, we can use that cancellation to get the X's away from the R. So if we know Z cancels X, whoops. Which side did you cancel the X on first? The right. So if we stick a Z on the right side of both of these expressions, which, by the way, we can only really do that if we have the associative property. Otherwise, there's kind of an implicit set of parentheses around this XRX that we don't necessarily know that Z can even attack that X because it's outside of the parentheses. But with the associative property, we can regroup that however we want to and let that Z and that X operate on themselves first. And when this X and Z operate on one another, what happens to them? They become E, right? But then on the right side of the equation, XZ, actually that becomes E also. And then what is XRE going to be better known as? Why is that?
Because anything with the identity is itself.
Yeah, that's E's whole purpose in life here, right? Is to be an identity. When it operates on anything, it leaves that thing unchanged. So now I've got a simpler equation, XR equals E. How do I solve that equation? Cancel the X on the left. How do I cancel an X on the left? That same Z. Right? So that's why we needed Z to be both the left inverse and the right inverse. Because if we didn't know that, we might have different ways of canceling those X's on the left side and the right side. So I get ER is equal to ZE. And what is ZE going to be? Z. After all, E is an identity. But then ER is just R. And so in the first equation, R is equal to Z is my solution. So I actually needed to know quite a lot of information to be able to solve an equation. I need to know what's my identity, right? What element do I have as an identity in the structure? And then I need to know how to cancel anything, how to get an identity by operating on, in this case, X. And I need to know that it works on the left, and I need to know that it works on the right in order to make this thing work. So we're kind of honing in on what are the necessities, what do we absolutely need to have in order to do algebra. Somehow we need to have an operation. We'd like for it to be associative, because if it's not associative, we don't know that we can just operate on this expression and group the X and the Z together. We might have weird parentheses things going on. We need there to be an identity that we can identify. Right? And once we know what the identity is, we also then need to be able to cancel anything in order to solve equations. And so if we have those things, it seems like we can do algebra. If we don't have one of them, then maybe we can still do some kinds of algebra, but we certainly aren't going to be guaranteed to be able to simplify absolutely any expression or to be able to solve absolutely any equation in one of these structures.